So, thank you all for coming. Whenever I'm a speaker, I hate it when the introductions are very long, because it cuts into my time, and that's a bad thing. So I'm going to keep this short, but I'm really delighted to welcome Steve Pulman, back to the department to give this year's Wheeler Lecture. As you maybe mostly know, this is the most prestigious event in the department's calendar, named in honour of David Wheeler, and we're delighted that Joyce can be with us today. Steve Pulman's one of those rare people who is both a real linguist and a real computer scientist. Started his career at UEA, and he was a member of this department between 1984 and 2000. I actually worked for him for a while in the 1980s, and I've always regarded him as, really one of my main mentors, if you like. Anyway, Steve went to Oxford in 2000, and as a professor of general linguistics, and then moved to the Oxford Computing Laboratory, in other words, the Department of Computer Science. For most of that time, he's actually had a parallel career in companies, or for much of that time he had a parallel career in companies, and he's now emeritus professor at Oxford, but senior NLP research scientist at Apple. He's done that since October. And his topic today is language learning and creativity. Thank you, Steve.
Okay, thank you very much. Well, I'm very flattered to be... Oh, yeah, you can clap if you like. Always welcome. Well, I'm very flattered to be invited to do this lecture, and especially with the connection with David Wheeler. David and I were colleagues for, as Anne said, for 16 years. And although our areas of research were quite different, he was always very supportive of the kind of stuff that I did, and just always a good person to talk to. So I'm very pleased to be able to give this lecture. So what I'm going to talk about is a mixture of linguistics and computer science, and the place I'm going to start is with some history of linguistics. As you'll know, one of the main figures in linguistics in the last 50 years has been Noam Chomsky, and his PhD supervisor was a man called Zelig Harris. And Harris was brought up in the tradition of American linguistics, much of which involved doing field work in North American Indian languages. And the situation that you were in was you were sent out to, well, typically unhappily, a reservation with no idea about the language, but lots of people who were native speakers of it, and you had to try to figure out what the grammar of the language was and how the language worked so that you could record it and hopefully help to preserve it. So Harris was interested in developing what he called discovery procedures for languages, based on the assumption that you just have a corpus of utterances from the language that are known to be, complete and grammatical, or actually, more realistically, probably an informant who you'd ask to produce such examples. And the idea was that you would build up the description of the language by doing some simple comparison and contrast exercises of sequences from the language. So you'd end up with statements like this. You define a noun as, this is English, of course, which is a really rare and difficult language. A noun is any X that appears in an environment where it's preceded by the and followed by either is or are. A verb is anything that appears in the environment where it's preceded by is or are and suffixed with ing. A set of tests like that will give you the basic parts of speech, as linguists call them, noun, verb, adjective, adverb, for a language. And you can use the same technique to describe the set of grammatical phrases of a language. So a noun phrase can be defined as something which will appear in an environment followed by a neutral verb like exists or something, where the result is a grammatical sentence. May not necessarily be a sensible sentence, but it will be grammatical. And we can carry on building up this hierarchical structure. So we can say that also if we've got an adjective, which we'll have defined by one of these tests, followed by a noun, that can be a noun phrase. And if we've got a noun phrase followed by a verb phrase, that will be a sentence. And we can do a pretty thorough job of building up the description of the language like that. The important thing for Harris was that these statements don't make any reference to meaning. They just need the information that this sentence is grammatical. That's to say that a native speaker of the language would say, yes, that sounds like my language, and not, it's gibberish. And working through these tests, we can end up with a set of statements which are a complete description of the language in principle. And we don't need very much to get started. We just need these basic notions like grammaticality and same and different environment, as I said, no reference to meaning. So in principle, at least, this process could be automated, although except in the case of a few bits of morphology, as far as I know, nobody has. Chomsky was Harris's PhD student, as I said, and like all PhD students, he kind of reacted against what his supervisor believed. And he also had a more kind of philosophical view about, well, Chomsky is a polymath, but he also had a more philosophical view. And what he'd noticed was that if you took this abstract procedure for discovering the structure of a language and tried to think of it as a theory of how people might learn language, one aspect of language at least, because we're ignoring meaning, then this was pretty much an implementation of a strict empiricist theory of language learning, where traditional empiricism sees the mind as a blank sheet with only a few very simple notions of similarity and difference, and everything that you learn comes in via the senses and is filtered by these simple principles of similarity and difference. So we can construe this Harrisian approach to learning language as a kind of empiricist theory. And what Chomsky argued was that if you did see it this way, you could show that it wasn't adequate, that this just wasn't enough to learn a human language, because there were lots of features of human languages that were just not capable of emerging from the data in the way that this discovery procedure needed it to be. So he demonstrated this with particular examples. There's a famous pair of sentences, John is easy to please, and John is eager to please. And the significant thing about this pair is that we've got the same sequence of parts of speech. We've got a proper noun, a verb, an adjective, an infinitive marker, and another verb. But the way that we interpret the sentences is quite different. So in the first one, it's John who is we're pleasing John, but in the second one, it's John who's doing the pleasing. So there's a quite radical difference of interpretation, but not correlated with any properties of the sequence of words on the surface that you could uncover, at least by these simple methods. The other argument that Chomsky, or another type of argument that Chomsky made, was that if you know a language, you know a lot about the relationship between sentences. If I give you a simple statement in English and ask you to turn it into a question, you'll do it. If you try to formulate the rule that lets you do that, you can come up with some quite simple things. So if we take the sentence like the man is tall, and we observe that the equivalent question is the man tall, we say, okay, I can write a program to do that. The program looks along the sentence for the first verb or the first auxiliary verb and moves it to the front of the sentence. And that will work. It'll work for lots and lots of examples, but it won't work for examples that are at all complicated. So if we take the man who was here is tall, and we go along it left to right looking for the first verb is was, we move that to the front of the sentence and we get was the man who here is tall. And that's not English. Any child will tell you that that doesn't sound like a good English sentence. The correct generalization is that you need a richer notion of the structure of sentences. You need the notion that the that sentences have subjects, that these can be actually arbitrarily long, and what you need to do is to find the first verb after the subject. So that means you need to know that sentences have this kind of hierarchical structure and that grammatical operations are sensitive to that structure. Children don't make the kind of dumb mistake that we made on the last slide. They automatically seem to go to the right type of generalization. And Chomsky argues that this shows that the empiricist approach just isn't right, that children are coming to this task with a head full of ideas already about what kind of thing they're going to find. And that's actually a better theory of how children learn language so quickly and so accurately that they already have a pretty good idea about the kind of things that they're looking for, and they're not just looking for every logically consistent hypothesis with the input. They have a set of a priori constraints on that. So this is a rationalist theory. This is a theory that says the mind comes with a fair amount of innate structure, and Chomsky argues, I don't actually know whether he's right, but so I just don't know anything about the area, but he claims that if you try to make the same assumptions about the way we learn visual perception, the same arguments would apply. You already have the structure there to do the right thing. Okay, so that climate of empiricism was what Chomsky was reacting against, and a particularly extreme form of empiricism was the psychological theory known as behaviourism, most closely associated with Skinner. This is a Skinner box. Some people here will have maybe even seen these. And it's an environment for torturing rats, really. So there are two kinds of... So the principle on which Skinner is trying to explain learning is in terms of conditioning. And the idea is that there's a particular stimulus, the rat gives a response to it, the response is rewarded or not. So there are two different kinds of setting. You can have a positive reinforcement, so the rat is hungry, it learns that by pressing a lever, some food will appear. You can make things more complicated and arrange it so that it's only when you press the lever when the light is on that you get food. And you can have negative reinforcement, so you can send a mild electric shock and it will learn to turn it off by pressing a lever. And with a bit of work, you can induce some quite intricate behaviour in rats and pigeons in this sort of way. Skinner tried to take that theory of learning, what you call operant conditioning, and explain linguistic behaviour in this way. So his avowed aim was to identify the variables that control verbal behaviour. Behaviour is sort of just observable stuff, and specify how they interact to determine a particular verbal response. Now you can see how in simple ways the conditioning stimulus-response theory might explain some bits of language behaviour. So I see this nice picture and I say Dutch, because I've learned a connection, or I might say pearl earring or something like that. Or I hear some music and I say, Mozart. Chomsky wrote this hilarious review of Skinner's book, Verbal Behaviour, which I recommend to you because it's one of the most sustained hatchet jobs I've ever read. And it also sort of introduces you to the kind of rhetorical tools that Chomsky will go on to use later on. Chomsky points out that, yes, there are some simple things that you could say, but I'm not forced to say Dutch when I see that picture. I might say something like, it clashes with the wallpaper, or it's not hanging straight, or I don't like oil paintings. Any number of things, most of those might be reactions to that stimulus, but I could say something not at all connected with it, like I've always been interested in trigonometry, where the connection between what you're seeing, the stimulus and the response, is not at all obvious. And what Chomsky pointed out in this review was that in Skinner's attempt to try to explain sophisticated verbal behavior in this way, took these notions of stimulus and response and reinforcement, which had a well-defined interpretation in the context of rats running in cages, but you extended them so much that they're really empty of any content in trying to explain our more sophisticated uses of language. So that one of many examples that Chomsky picks out is an account by Skinner of how people might interpret something like the telephone is out of order. So what point is there in saying that the effect of the telephone is out of order on the listener is to bring behavior formerly controlled by the stimulus out of order under the control of the stimulus telephone? What laws of conditioning hold in this case? What behavior is controlled by the stimulus out of order? And more generally, what Chomsky argued was that behaviourism is incapable of explaining what Chomsky calls the creative aspect of language use, which I'll say a lot more about, but the ability of any competent speaker of a language to produce completely new utterances, independent of any local stimulus or local context, but which are appropriate to the context. And the behaviourist notion was simply incapable of doing that. Okay, so here's more about the creative aspect of language use. It's language use that's unbounded. We can produce a potentially infinite number of new sentences. Every one of us every day hears or creates a sentence that we've never heard or created before. It might be similar in some respects, but if I give you a completely new sentence, you can understand it. It's largely stimulus-free. Clearly, to some extent, what we say is determined by where we are and what the local context is, but it doesn't have to be. And also, what we say is, in general, appropriate to the situation. You can find examples of each of these independently, so it's easy to produce lots of new sentences, it's easy to produce stimulus-free sentences, and it's easy to produce things that are appropriate to the situation. It's all three of them together that it's difficult. One of the interesting things that Chomsky also pointed out was that in the 17th century, the sort of flowering of rationalist thought, these properties were essentially regarded, particularly by Descartes, as criterial for the possession of actually having a mind. And here's a rather inelegantly translated quotation from Descartes, where he points out that you just could not conceive of building a machine to use language the way people use it. Furthermore, that no animals are able to use systems of communication that have this property of creativity. And more importantly, that this is not connected with general intelligence, as he puts it. So a machine could not arrange its symbols or words variously so as to appositely to reply to what is said in its presence, as men of the lowest grade of intellect can do. So even stupid people can use language properly, and machines can't. Okay, let's move on to the Turing Test. Turing famously wrote a paper on intelligent machinery where he proposed to say, look, we've got these things called computers or machines more generally, and people keep asking, can these things think? Well, Turing thought this was a fruitless question. He proposed to say, let's instead turn this into an operational test to see whether a machine could display something that we might describe as intelligent behavior. And the way he sets this up is you need to abstract away from the fact that machines don't look like people. So we'll assume that we can only talk via teletype or email or something. And the test is you've got a human talking to two things. One of them's a machine and one of them's a person. And if the human can't tell which is which after a reasonable period of time, and there are different versions of this, sometimes it's 5 minutes, sometimes it's several hours, then we'll say that the machine is intelligent, because operationally it's indistinguishable from something that clearly is intelligent. People have argued about whether this is a good test for intelligence. I think it's actually a very good test. And also, I think it's sensible to try to get away from the can machines think kind of question. The examples that Turing gives of the kind of conversations he imagined are quite amusing. So one of the things is that the machine is assumed to be able to speak English. That's really easy to build into a machine, as we've discovered in the last 50 years. But also be intelligent in the usual sense of being able to solve chess problems and mental arithmetic and so on. But also, and here's an imagined conversation, to be sort of fairly creative in its language use in the Chomskyan sense. So I'll read this. So the human says, in the first line of your sonnet, quite why it needs to distinguish a machine from Shakespeare, I don't know, but in the first line of your sonnet, which reads, shall I compare thee to a summer's day? Would not a spring day do as well or better? Machine, it wouldn't scan. How about a winter's day? That would scan all right. Shall I compare thee to a winter's day? Yes, but nobody wants to be compared to a winter's day. Would you say Mr. Pickwick reminded you of Christmas? In a way. Yet Christmas is a winter's day, and I do not think Mr. Pickwick would mind the comparison. The machine starts to get a bit sulky here. I don't think you're being serious. By a winter's day, one means a typical winter's day rather than a special one like Christmas. Now, if I had a conversation like that with a machine, I'd say, yeah, you're smarter than I am. Right. Notice that the content, as well as the fantastic linguistic ability, the content presupposes an enormous amount of very sophisticated cultural and literary knowledge. Turing, had lots of experience at writing programs and clearly thought, how on earth would I ever be able to write all that stuff down in a set of programs or encode it in some kind of data? It's probably not going to be possible. Let's see whether we can figure out how to teach a machine this, or get the machine to learn it all. How is the learning going to take place? Well, like most people at the time, I think Turing was a thoroughgoing behaviorist and empiricist. This is what he says. This is not from the famous paper, this is from a later one. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. Presumably the child brain is something like a notebook as one buys it from the stationers. Rather little mechanism and lots of blank sheets. So complete empiricist point of view. There's a bit more. I put this in because it's just so quaint. The criterion as to what would be considered reasonable in the way of education cannot be put into mathematical terms, but I suggest the following would be adequate in practice. Let's suppose that it's intended that machines should understand English, and owing to its having no hands or feet, and not needing to eat, nor desiring to smoke, it'll occupy its time mostly in playing games such as chess and Go and possibly bridge. I suggest that the education of the machine should be entrusted to some highly competent schoolmaster. The machine is going to have a memory, and if some new situation arises, it's going to consult the memory to see what it did last time and what worked best. How does it know? What's the definition of working best? Well, Turing sees there must be some notion of a favourable outcome, and he says this, there should be two keys which can be manipulated by the schoolmaster and which represent the ideas of pleasure and pain. Okay, so this is straightforward Skinnerian conditioning. You got that wrong. Deep learning. We need something that's going to help us get a machine to learn to behave in this intelligent way. And the latest, greatest approach to this is deep learning, some of which has been around for actually quite a long time. I'm not going to go in much detail, but let's start off with a neural network. This is a well-known technology, widely used by many people I can see here in this room. It's a network of nodes with edges between them. There are weights on the edges, and you train it by giving it an input, which is typically a vector of numbers, one for each of these nodes. You multiply those numbers by the weights through to a hidden level of more neurons. Do the same thing again until you get to the output. You do some stuff to the output to make it look a bit like a probability. And if the answer's right, you leave the weights as they are. If the answer's wrong, you kind of propagate the error back through from the output through to adjusting the weights as you go. And you do this over and over and over again, and eventually the weights learn to give you the right result you have given a particular input. That's traditional neural networks. Deep neural networks are just the same thing. They've got to have at least one more hidden layer, according to one of the big figures of the movement. In language processing, there are lots of different flavors of this. In language processing, typically the type of neural networks used are things called recurrent neural networks, which have a little sort of loop in them. And the idea is that these are able to take into account not just the input, because we're typically processing something from left to right, they take into account not just the input at a particular point, but what the network said about the input at the previous point. And so to get that to work, we kind of unroll it. We make lots of different copies, one for each thing in the sequence that we're processing. And the rest of the training is almost exactly the same. You put the input in, you see whether it gives you the right results. If it does, you leave it alone. If not, you propagate the error back through the system, adjusting the weights as you go. A particular type of recurrent neural network that's currently in its various flavors, the method of choice in language processing is something called contradictorily a long short-term memory network. This is just like a recurrent network. It has some fancy stuff in it for helping it to remember or to learn how much of the previous input to remember and how much to ignore, and how much to pass along to later stages in the decision. So the internal structure of these things is quite complex, but it's the same sort of basic idea. Another type of deep learning is a version of reinforcement learning, and I'll start with what I call traditional, 10 years old, one of the simplest forms of reinforcement learning called Q-learning, which is a direct implementation of the Skinner approach. The idea is that you learn rewards or punishments are associated with particular actions, and given a set of training data and some fixed rewards and punishments, you will learn what the optimal sequence of actions is to get the greatest reward. There's a very, very simple algorithm. You just represent the thing as a big network, choose a state in that network, select an action, see what the reward is. If it's right, we leave it. If it's not, we adjust the weight by looking a bit ahead and see what we should have done instead. And it's easy to see this from a picture. So here's a simple network of possible states. We've got a winning state, F, which will get you $100, and a losing state, which won't get you anything. And by going through that algorithm, what happens is, after a few iterations, the rewards kind of propagate backwards, so that we start seeing that paths that lead to a losing state don't get any reward associated with them. Paths that do get some reward, and you keep on doing that, and it'll eventually settle down to something like this, where, as you can see, if you just choose the highly valued ones, you'll get to a winning state every time. Now, there's a sort of analogy here between the neural network as well, that you've got this notion of success or failure at the end, and you're using that to train the network by pushing that experience back through the earlier stages of the network. And in the sort of more fancier, deep reinforcement learning systems, the kind that's embodied in things like AlphaGo, that is taken literally. So a lot of this technology is just a combination of neural network concepts and the basic reinforcement learning. There's probably too much detail here for this particular thing, but it's the same basic idea. You've got an idea of success or failure, and you use that to train the system to learn what to do at every particular stage. What kind of learning theory is this? Well, all of these deep learning theories are, I think you'd have to say, completely empiricist. There's no a priori knowledge involved. It's just a bunch of numbers and weights between things. There's typically no task-specific, because there can be, but typically there's no task-specific tweaks to a network. Everything's learnt by repeatedly exposing the system to labeled training data, and lots and lots and lots of it. So, for example, current speech recognition systems are trained on more examples of spoken language than a human would hear in several lifetimes. So it's a thoroughly empiricist approach to learning. Everything is supposed to come out of the data. So the obvious question at this point is that, given what Chomsky's position was about the adequacy of these systems for learning human language, how likely is it that we could use deep learning methods to teach a system, or for a system to learn enough to be able to pass something like the Turing Test? Well, let's look at some of the things that Chomsky thought empiricist approaches couldn't deal with. So the first of these was the property of structure dependence. The idea that when you learn properties of a language, you learn about implicit hierarchical structure and use that rather than string manipulations. Well, there has been quite a number of influential papers in deep learning that have looked as if they have partly solved this problem. So there's a famous paper called Grammar as a Foreign Language by the Google folk a few years ago, which showed how you could do full-blown parsing, in a sense, using just a sequence-to-sequence model like the LSTM, the long short-term memory system that I showed you earlier. It involves a bit of a trick. So typically you represent the hierarchical structure of a sentence with a tree diagram like this. So this says, John has a dog is a sentence. It consists of a noun phrase and a verb phrase. The verb phrase consists of a verb followed by a noun phrase. We can take a tree like that and produce a logically equivalent representation in terms of labeled brackets. So we just label the beginning and the end of the constituent. So that's a left S bracket closed off by a right S bracket. That's a left NP bracket closed off by a right NP bracket. And you can translate between these two notations. The important thing is that that is a tree. It's a structured object. That's a string. Even though implicitly it contains the same information, it doesn't explicitly contain it. So what this model did was learn how to take a sentence in and produce one of these strings of labeled brackets, sort of like this. So you give it John has a dog, and it says, the correct sequence of labeled brackets for that sentence is this. They trained it on a fair amount of data, 11 million sentences or so. The 92% score, F1 score on this particular benchmark data set is very good. So it's a really impressive result. Has it really learned the notion of hierarchical structure? Well, I'd say no. I mean, if you think about it in computer science terms, the language of labeled brackets there is a context-free language. So it has particular properties if you're going to have well-formed sequences of labeled bracketings. And I don't think that this sequence-to-sequence model learns that at all. It has no idea that every left bracket should be matched with a corresponding right bracket. It learns to do it, but not completely. So when you look at the error pattern, they're all to do with missing right brackets. So it's actually just not learned that simple generalization that you need to match the brackets up. There's been some other work rather similar, looking to see whether you could get these LSTMs to learn the grammatical structure that Chomsky was talking about, the structure, the agreement between nouns and verbs. This was a very clever idea. So take a sentence like, the students submit a final project to complete the course. So the students is the subject, and the verb submit has to agree with it. Okay? So the students submit, not the students submits. So both have got to be singular or both plural. You can make these sentences more complicated so that the agreement between the subject and the verb has some other stuff in between. The students enrolled in the program submit a final project. Okay? And now we've got what they call they call it an attractor, but I think that distractor is a better idea. We've got a singular noun immediately before the verb. We can make them more complicated. The students enrolled in the program in the department submit. The students enrolled in the program in the department where my colleague teaches submit. Okay, so these are getting harder and harder. The machine's got to learn a longer stretch of dependency. Actually, it doesn't seem to do too badly. So with 4 intervening distractors, the error rate on their particular test set was only about 17%. And it turns out that actually, people are going to get this wrong some of the time as well. So that's quite impressive. Some colleagues in Gothenburg repeated these experiments and with a lot more data. And also, they tried to tease out the question of what exactly is being learned. Because, just going back to the previous slide, it might be that what the system is learning is whenever you see students, you'll see a verb like submit somewhere near. So I've seen students, I'll just hang on and wait till a submit comes along. So that's not learning grammatical structure, that's learning a lexical correlation. So they tried to tease apart whether that was the case by getting the system to learn based on just parts of speech. So or the sentences where most of the words have been replaced by their parts of speech, so that you're effectively having sentences like the noun is adjective, noun, blah, 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 but with enough information that you can figure out the agreement. And what they discovered was that the system really didn't do very well on this at all. And what they surmise is that actually what was happening was that it was learning these lexical correlations between words rather than structural properties of sentences. This is a hot topic. A couple of months ago, the Facebook group repeated these experiments, and they had a different way of trying to get at these two areas. One used ordinary sentences, and in the other case, they used a set of nonsense sentences, so produced automatically from a corpus. So we have a good sentence like, it presents the case for marriage equality in states, blah, blah, blah. And here the task is slightly different. What we've got is 2 verb phrases, and the verbs of those verb phrases must be the same in number. So we've got presents and states. And they just randomly replace these with different words, so you get things which are grammatical but nonsensical, like it stays the shuttle for honesty, insurance, and fines, blah, 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 blah. So the idea is if it does as well on the nonsense sentences as it does on the sensible sentences, then it must be learning something structural, not something that's dependent on lexical relations. And they found that although the performance on the nonsense sentences was a few percentage points less good than on the grammatical sentences, the same was true for people. And they also did an experiment where they had human subjects do this for Italian, which in some ways is a lot easier because Italian has a lot more agreement morphology than English does. And for their model actually was almost as good as people. So they're claiming that what these systems are doing is learning something more like abstract structural dependence. Of course, from an engineering point of view, that's not really necessary. What you could do, if you wanted to get these systems to learn something like human languages, is give it more a priori structure, build into it a stack or the right kind of structure. And in fact, that's exactly what some of my former Oxford colleagues, who are now at DeepMind, have been doing and getting, as you might expect, fabulous results because they're building in the a priori structure to this. I should say something about word embeddings. I mentioned them there. Word embeddings I think are one aspect of deep learning that will solve a problem that was raised against the Turing test by a philosopher whose name was Robert French, I think about 20, 30 years ago. Let me say first what word embeddings are. They're a way of representing a word by a sequence of numbers. And you get these numbers by using a neural network. Well, there are actually several different ways of doing it, but one way is by using a neural network. And you create a set of negative and positive examples. A positive example is a grammatical stretch of text. And the negative example is that same stretch of text with one word randomly replaced. So something like, photographer visits Syrian refugees in, that's a grammatical stretch. Photographer magenta Syrian refugees in isn't quite grammatical. And you just train a network to distinguish the two. So the training objective is just to give a better score to the positive than the negative. And you do this in the usual way, propagating the errors backwards, but the input layer start out as random vectors for individual words, and you propagate the errors back into them so that eventually those numbers learn the context of particular words. And this works astonishingly well. So here are some examples. One of the ways you can test out this stuff is by looking at what words come out as semantically similar. So here, from a famous experiment a number of years ago, you have the vector for the word France and say, okay, what are the nearest vectors by some measure like cosine distance? And the answers come back Austria, Belgium, Germany. That's pretty good. You know, it could have been magenta, typewriter, teapot. Verb like scratched, the nearest ones are things like nailed, smashed, blah, blah. But the great one, the widely quoted one, is that you can do arithmetic with these things. So if you take the vector for king and subtract from it the vector for man, and then add the vector for woman, and then say, what a pre-existing vector is this one closest to? The answer comes back queen. This, which is pretty good. Take Paris, take away France, add Italy, and the resulting vector is near to Rome. Sometimes it's not quite right. So if we start with the vector for sushi, subtract Japan and add Germany, we get bratwurst. Well, that's probably pretty good. But if you add France instead, you get tapas, which is the wrong country. But, it's still pretty impressive. So these word embeddings seem to capture something meaningful. One of the arguments against a machine ever being able to pass the Turing test, advanced by French, was on the grounds of what he called subcognitive processes, sort of processes involving language understanding beneath the level of consciousness. In particular, these associative memory problems, tests. It's a well-known fact that if you're given a word, words that are semantically related to it will kind of somehow be primed. They'll pop up more easily. So if I give you the word doctor, and if I have a setting where I give you a word, and then I give you another word, and you have to say immediately, is this a real word or not? Then I prime you with doctor and give you a word like patient, you'll say yes very quickly. If I give you prime you with doctor and give you teabag, you might say yes eventually because it is a word, but you'll have to think about it. And if I give you a nonsense word like Danbridge, you'll take even longer. Okay? So lexical decision tests. Another aspect of this was neologisms. So French asks you to imagine the word flugblocks and to decide what is it. Is it the name of a new breakfast cereal, a new computer company, or large air-filled bags for the feet used to walk across water? And his judgments are that the first two are not. And so I should say, incidentally, that when he was writing, the word blogs didn't exist, so our judgments might be a bit different now. But I think you could actually get this out of word embeddings. So certainly, if I do you think doctors have more in common with nurses than they do with tea bags? look at the vectors for these things and they give you the answer. You could, as well as doing embeddings for words, you can do it on sequences of characters. So I think you probably might be able to say that flog-blogs was nearer to the vector derived from large air-filled bags for the feet than it was for new breakfast cereal. But it's probably too late for setting MSc topics for this year, but that would be a nice topic for somebody to do. Okay, I've talked about the creative aspect of language use and the Turing test. And I think that while they're clearly connected, they're actually quite they're distinct. So remember that the creative aspect of language use involves three properties. It involves utterances being unbounded. We can produce a potentially infinite number of new sentences. They're stimulus-free and appropriate to the situation. If we were going to build a machine to display these properties, we'd clearly need to have some kind of scientific understanding of what goes into them. And Chomsky, right from the start, has been extremely pessimistic about this being possible. If you think about what is involved in these things, it involves all the kind of traditionally hard philosophical questions. It involves notions like freedom of the will, intention, choice, decision, things that philosophers write about, but which we have no real scientific insight into, except in extremely contrived laboratory special conditions. So Chomsky, in one of his well-known books called Problems and Mysteries in Language, classifies this as a mystery. This is not something that we're ever going to be able to do science about. And his analogy is, the reason for this, he thinks, is that our brains are just not constructed in the way needed to form scientific theories about these things. It's like asking frogs to do nuclear physics. They just don't have the brains for it. If we could build a system that had this property, it's clear that it would be able to pass Turing's test. So the question that I wanted to get onto was, how far away are we from this? Well, for unboundedness and novelty, we've sort of got some of the story. We know how to build or to learn recursive mechanisms of syntax and semantics that will produce or will characterize an infinite number of distinct new sentences along with their meanings. Of course, in the context of the creative aspect of language use, these sentences have got to express some kind of thought of ours, and we have no idea how to connect these symbolic representations up with thoughts. We don't know, for example, how to, what factors would prompt us to start a conversation. And for some special cases, we can think of, well, if you walk into a room, you pretty high probability that you'll say hello, but that's a very limited type of conversation. Now, it's tempting to say, well, okay, this sounds like a reinforcement learning problem. You're in a state. What's the next best action to do? And in the abstract, it probably is. But, the chances of being able to build and train a system to do that is very, very complex. Actually, in one respect, the Turing test, I think, turns out to be quite a bit simpler than developing the creative aspect of language use stuff, because in Turing's scenario, you're very much fixed to the question answering paradigm. You ask the computer a question, it gives you an answer. So all the stuff about initiating conversations isn't needed. That's already set up. And what you're using language for is also relatively restricted. So there's none of the kind of, at least in the examples that Turing gives, there's none of the kind of social aspects of language use that we also find it difficult to do scientific theorizing about. What about the stimulus-free property? Well, when Chomsky talks about stimulus, he really seems to be talking about it in the Skinner stimulus response. And I think that where the stimulus is in the local context. And yes, it's clear that most utterances are free of stimulus in that respect. But is it plausible that they're free of any sort of stimulus? I mean, surely not. That would just be a random and unconnected utterance. The problem is that the stimuli that an utterance is reacting to is something that is going to be private to the speaker very often, not obvious from the context. It can be almost anything that has, anything that has happened to the speaker in his or her lifetime. So if you were trying to produce a model that figured out what to say, you'd have to train on an awful lot of data. Though I think that's what Turing had in mind when he was talking about the teacher teaching the machine. Appropriate to the context, I think we're a bit better off here. There's actually some quite interesting but completely unimplementable linguistic work relevant to this, the Wilson and Sperber's relevance theory, which is, I'm a great fan of this, though many people aren't, I should say. But it's a theory of what they're trying to do is to get a theory of what makes an utterance relevant to a particular situation. And their main insight is that the relevance of an utterance is connected with the amount of information you can get out of it and the amount of effort you need to put into to getting some out. So relevance is a trade-off between processing effort and the amount of information you can gain. And here's a simple artificial example to illustrate what they mean. So the situation is Mary, who dislikes most meat and is actively allergic to chicken, asks, "What are you serving for dinner?" And it's chicken, and John knows it's chicken. And John can say one of three things. He can say, "We're serving meat," or "We're serving chicken," or either "We're serving chicken," or 13 is not a prime number. Okay, now, clearly, B is the relevant, most relevant. Why? Well, because "we're serving meat" gives an amount of information, but not the right amount of information. C gives the right amount of information, but you have to do a fair bit of logic to get there. So that's an artificial example, but I think the intuition is exactly right, that producing a relevant utterance is this nice trade-off between processing effort and amount of information. I wish it was as easy as that, though, because in order to do any of that kind of stuff, we effectively need to have solved the general AI problem of how do you reason using lots of non-linguistic knowledge. So here's another very simple example. Peter says, "Did John pay back the money he owed you?" Mary, "No, he forgot to go to the bank." Okay, why is that relevant? Why is about the bank relevant? Well, because you go through a chain of reasoning. Banks supply money. Well, at least they used to. No bank, no money. And if you've got no money, you can't pay something back. There's lots of other inferences you could make from that. And in order to have some kind of computational account, we'd need to be able to rank different inferences in terms of utility or information content or something like that. We also need to have some way of comparing processing effort. We can sort of do that for artificial systems, but we don't really know how people behave in that respect. And the other thing that I haven't mentioned in detail, but which is necessary for this, is in order for me to produce something that's relevant, I need to know what you already know and believe. So I need to have a mental model of your mental model in order to be able to do those calculations. Okay, so I've argued somewhat along the following lines. Empiricist learning theories don't seem to be capable of learning languages that have the properties of human languages, provisionally. Maybe the deep learning chaps will solve it. If you're going to get a machine to pass the Turing test, it's not going to be able to learn for itself then, in that case, if one of the things it needs to learn is how to use language properly. Nevertheless, so the reason for that is because all of the paradigm of learning that we have at the moment is all supervised learning. It's somebody provides examples correctly labeled for the machine to learn from. I think Chomsky is essentially correct about many of the properties of language. But I don't think that that's necessarily a barrier to building systems that can learn language in that sense. You just need to build that a priori structure into the learning systems. And there's a very interesting YouTube video, a conversation between Chris Manning, who's a computational linguist in Stanford, and Jan LeCun, who's one of the big figures in deep learning, where they talk about exactly this. And it actually seems to be happening as we speak. People are trying to build a lot more a priori knowledge into these systems. Creativity of language use in Chomsky's sense, if you could build a system that displayed that, it would certainly pass the Turing test. I think actually the Turing test is less difficult. I think we probably will be able to build one that passes the test properly. And I discount the kind of Loebner Prize examples. You know, there's this competition, so called the Turing test, which you can win quite serious money actually with your systems. But the way it's set up is not really the Turing test. So I don't think it's been passed. How long would it take? I don't know. I mean, Turing was talking about 100 years, 70 years ago. So that gives us another 30 years, which might be enough. Why can't we build a system that is going to fully display the creative aspect of language use? Well, I think Chomsky's essentially correct. We don't have the mental equipment to get the scientific understanding of how that works. And if we don't have the scientific understanding of how it works, we won't be able to engineer systems that display that understanding. So we come back to really difficult philosophical problems: choice, free will, intention, and as Chomsky said, you can learn more about that by reading a novel than you can about reading science. That's all.
So that was spectacularly good timing, and we have a quarter of an hour for questions, if somebody would like to start. So we have, shall we, since the microphone is there, shall we go you first?
Hello, thank you for your talk. That was very interesting. I have sort of three short questions. One is, well, maybe one a bit longer. So you say that we need to we can't learn these things from data, but if we build in a priori structure into deep learning, then it does that. How is that different from the human brain? Presumably, we have the a priori structure to handle language, which is how we learn language.
Yes, it's not different from the human brain. I agree with Chomsky that there's a lot of a priori structure there.
Cool. Next one is the Turing test really the appropriate test? Like, so this is a test designed 70 years ago by Turing, very appropriate in spirit, but is this really the appropriate test for artificial general intelligence in language? Or maybe we want to make something more specific, more controllable. Like, so it seems that the Turing test is about tricking the human into not being able to distinguish between a machine and a person, but maybe there's something else that we can have the machine demonstrate without necessarily having a tricked person there.
Well, maybe, but I think Turing was just trying to avoid, questions that he didn't think were fruitful. He said, well, let's just agree that if a machine could behave like this, we'd call it intelligent. So I think, that's fine. Now, there could be different things. Can you create a creature that seems like it's got a mind? That's much more difficult, and that would need a different test.
Okay, and regarding the scientific tools, so are you arguing that we inherently cannot understand the mind, or yet understand the mind?
I wouldn't presume, but Chomsky thinks we inherently can never understand the mind.
Okay, that's weird, because 400 years ago we didn't know how the sun worked, and now we do.
But that's a physical system, and
so is the mind. So is the mind. It's a physical system. It's here. Got a bunch of neurons here.
Well, that's one way of looking at it. But I think the evidence, in 400 years we've learnt a lot about the sun. In 2,000 years we've learnt nothing about the mind.
We didn't have the scientific tools.
Where are they?
Further, maybe.
Well, I think we just have to. It may be possible that progress in neurology will give us that, but it remains to be seen.
Okay. Thank you.
better, right? Now it's on. A few slides ago, you said that to pass the Turing test, you only need to be able to answer questions. Now, I'm a bit dubious about that, because if I was having a conversation with someone and they never did anything but answer my questions, I would say, this is a pretty odd sort of human. There's something really funny going on here. So I want to ask you if you really are making the claim that you can pass Turing tests by only answering questions.
No, I wasn't very precise there. But the test is, person A says something, the other person or the machine says something, and they go back and forth like that. So it's not a general kind of conversational setting in the way that we're having now. So I think that's all I meant, was that it's more restricted than general use of language in social situations. I mean, Turing seems much more, there's much more about the content of what the machine says that seemed to be important to the passing the test. For me, the machine could not know about anything, but if it used language very well, I'd be jolly impressed.
So what you're saying is that if I was communicating with a machine that was operating in that way, I wouldn't be able to tell whether it was a human or not. And I think I don't agree with you about that.
There's a question down here.
So there are some theories about kind of modeling intention modeling, basically, so like RSA, for instance, or Bayesian theory of mind. Do you think they get us some of the way towards like understanding these mechanisms of like choice and free will, at least enough that we might be able to pass the Turing test?
They can certainly shed some insight, but I don't think that they're going to get us very much closer to that. Because again, if you think about how you build a system using that, it would have to be in such a constrained domain, at least given our current understanding. It wouldn't have the kind of flexibility and generalizability that you'd need to be part of the Turing test, I think.
Okay, I have a question, but not for you. For you. Yes. Joyce, back in the good old days when I understood everything, we had a David Wheeler with us who did understand everything, and it was a joy to work with him. My question is, would David be, in your opinion, attracted to this work rather than the stuff he used to do?
No, I don't think so, because I think he would have regarded it as too difficult. Yes, he could assess whether something was doable. I think that was his great advantage to research students, is that someone came with the proposal. He was very, very quick and knowledgeable to point out whether the problem was doable, or reasonably likely to be doable. But
very important property in a PhD supervisor.
What's your opinion about how much actually creativity is related not with particular language or any languages, but observed world or environment and the knowledge that we have there that is not particularly related with given language? And have you observed any good works related with stuff?
I'm not sure I understood that.
How much of the creativity that's going to be seen during the conversation with the dialogue system is based actually on the knowledge of coming from the environment or the world that we're observing, rather than from just playing around with the language? Obviously, that part is also important.
Okay. So if I understood correctly, it's how much is to do with purely linguistic creative manipulation and the integration of that with non-linguistic knowledge. Well, I think the integration with non-linguistic knowledge is the important part, because actually it turns out that quite a lot of what you might think of initially as language understanding is actually world understanding. The two are very tightly integrated. So even just things like resolving ambiguities in sentences, you need to know an awful lot about the world to figure out what the appropriate interpretation is.
Thank you. So one of the things that you didn't talk about is
of
the way
those.
is the way in which these computational models of language are being used. Well, they're being used to understand how language is instantiated in the brain, and it's quite interesting, I think, because the argument's going both ways. So if we use these models to test against brain data, for example, are we finding out about how the brain works or how the model works? And I think that's a really, if we could build on that, I think it would be really interesting, because at the moment, we don't really, because we don't have an understanding of how language is instantiated in the brain, we're grasping at ways of trying to model it in order to be able to develop accounts. But as I say, it's a two-way street.
Yeah.
And I think that's a very interesting two-way street.
Absolutely. And in fact, the reason I first got involved in computational stuff was because I saw it as a good way of testing linguistic theories, to build something. If you can build something that does some linguistic task, you at least know you've got a kind of logically coherent account of how that task could be performed, and then you can go on and ask, well, how is it performed?
Yeah, and as long as you have to give a lot of weight to the results that you get, and not just dismiss them.
Curious how optimistic you are. In your second paragraph here, you say it's not impossible that the right a priori structure could be built. But do you think that when people try, it'll work really soon, or is it 30 years?
It's not a good idea to get involved in making predictions of that sort, I've discovered over the years. A long time.
In which case you may not want to predict the answer to this, but we often talk about, we're thinking in terms of, can we make a machine that's as good as a human at answering these questions? In some areas, such as acquisition of knowledge, machines may well overtake us. So do you think to pass the Turing test we'll have to build in fallibility so that they are more like humans, that it's not a doctor that knows the diagnosis for every disease on the planet or something?
Well, I don't think that, because the Turing test was a test, an operational test for whether a machine would be intelligent, not whether a machine would be human-like. And in fact, in many ways you want your machines not to be human-like.
In which case, is it a good test? Because you are testing to see whether the machine is human-like, but in the Turing test, aren't you?
So I think that Chomsky and other scholars demonstrated convincingly that there are many aspects, as you said, of language that can't be learned from the data. So I'm really interested in this idea that we can build this kind of a priori structure into DL models or other algorithms. So, for example, do you think that evolutionary algorithms could approximate something like that? Like, could the environment or some kind of external factors affect the way we categorize the word or organize our linguistic knowledge? So how can we build this kind of structure into our models? Do you have any suggestion for that?
The honest answer is I don't know. I mean, things like genetic algorithms in particular have been very unsuccessful in learning most language properties. And I think the reason for that is because grammatical systems tend to be kind of global in nature. So if one little bit's missing, nothing will work. Whereas genetic algorithms sort of make incremental tweaks. The whole thing needs to keep on going for evolution. So I think the current crop of genetic algorithms just fundamentally unsuited to that kind of problem. But maybe some other type of learning approach, evolutionary learning approach might work. I don't know enough about it, I'm afraid.
Your example conversation, the fanciful, shall I compare thee to a summer's day, as you pointed out yourself, this is setting a pretty high bar because you don't know many people who would be capable of having that conversation, and I don't either. Perhaps it's because, assuming that we are having conversations within a cultural context, nobody is particularly interested in having computers act within human social context anyway, because we weren't planning to fall in love with them or marry them and so on. What we really want is to pass Turing tests in computational contexts where their behavior would be completely appropriate. In which case, I'd argue that we've probably we've passed the Turing test already because when I'm on Twitter, I really have no idea whether a tweet is coming from a human or a robot. They've created their own context, which has dumbed us down to the level that they can pass the test pretty easily.
I was wondering more specifically about what we mean by the creative use of language and the way, say, language is used in literature with figurative devices or kind of unusual combinations of words. Can we train a machine to, first, not only can we train a machine to use a metaphor, but to, if it has a choice between that mode of expression and a more direct mode of expression, what would make it choose the indirect mode of expression? I don't know if creativity is necessarily equivalent with indirect expression, but there is a link there. And when you were discussing the nonsense words, I suppose kind of creative language could be described as nonsense if defined strictly as a deviation from standard language. So how would it discriminate between what we could discriminate between nonsense and, say, something that is effective in a non-standard way? Can a machine discriminate between that?
Well, if the answer is can they, at the moment, it's no. Will they be able to some extent? And people have done some small-scale experiments on things like interpretation of metaphor. But with all of those things, again, it's really the interplay of linguistic knowledge with non-linguistic knowledge, which is the fundamental problem, and we just don't have a very good understanding of how to deal with that, or even how to encode a lot of the non-linguistic knowledge. But it's an interesting question, and several MSCs worth of work on it.
So thank you all very much for all the questions. I think we should draw this to a close now. I've got one last thing to do, which is to present you with the certificate that says you've given this this distinguished lecture. We have framed copies of all of these certificates in the corridor in the department. If you would like, this is your copy, if you would like your copy framed, then we can do that, or if you want to just dispose of it quietly, you can do that. Just don't tell me. Yeah. So thank you very much, and thanks very much.